guys, welcome back. Today we are doing 1.2, functions and their properties. Not gonna lie, this is a big section. There's a lot of information, vocab words, a lot of things that we will need to talk about. So we're gonna go ahead and get started. All of them you've seen before. I know you've seen them in Algebra 2. It's just kind of a little refresher in how to write answers and things and such. So let's talk about first function, domain, and range. And so a function from set D to set R is a rule that assigns to every element D one unique element in R. So basically for every one domain, for every one X value, there's only one Y value. So our X values can only go to one Y value. If our X values has two possible Y values, not a function, okay? And then so domain is all of the X values, and then R is the output, which is the Y value. So domain equals X, range equals Y. So if we look at this graph right here, and so one of these is not a graph of a function. So one of these is not a function. Well, which one? How can we determine if something is not a function? So we're gonna do the vertical line test. Okay, vertical line, vertical means straight up and down. So we're gonna take our pencil and we're gonna travel it along our graph, okay? If our graph touches our pencil in two spots at the same time, it's not a function. That one, it doesn't, so we're good. Yes, it's a function. B, we're going, we're going, we're going. Look, it's not touching twice. Good, we're a function. If we look at C, we're going, we're going. So if we look at this vertical line right here, just for that example. On that vertical line, our graph touches it at 1, 2, 3 different spots. Okay, we did it like right here, right here. It's touching, on that vertical line, it's touching in 3 different spots, okay? So by definition, for every X value, we'll say this X value of, I don't know, right here, that's negative 0.5. We have a Y value of 0.25. We have a Y value of 2, and we have a Y value of negative 2. Okay, so for our X value, we have 3 different Y values. So by definition, not a function. Okay. Now let's talk about finding domain of a function. And I'm going to show you with the equation, and I'm also going to kind of back that up with the graph. Me personally, I like to graph it. I'm a very visual person. I like to see the graph. Desmos is going to be your best friend. Okay, use Desmos. So with this, but I'm going to also show you to back it up with how to find it with our equation. So A is A, B is B, C is C. So it says to find the domain of these functions. So we're looking for domain. Remember, domain is X value. So we're looking for what are the possible X values. Okay, and it also, we have to think basically where we have like limitations on your X. So if you think about a square root, okay, we cannot take the square root of a negative number. So that is, if we see a square root like an A, we have to think this inside under here cannot be a negative number, okay? We also need to think about with fractions, your denominator cannot be 0. Okay, so those are some limitations that we're going to kind of take into play. So algebraically, if we look at A, we know that this cannot be a negative number. So that X plus 3, it has to be greater than or equal to 0. Because underneath it, we can take a 0. Square root of a 0 is just 0. So this right here underneath needs to be greater than a 0. If we solve for X, subtract 3. This is saying X, all of our X values have to be greater than or equal to a negative 3. And so looking at our graph starts at a negative 3, and then it goes up. So all of these X values that we have for our graph are greater than negative 3, okay? And so to write that as our solution set, we're going to say it goes from negative 3, which is included because it can be at 0, negative 3, 0. and all the way up to, this is going on forever. So positive infinity, because it goes towards the positive x values. Infinity is not included, so it's a parentheses, okay? I think it's personally easier to visualize from your graph. However, we need to be able to relate this algebraically, okay? B, if we have the square root of x, and then we have x minus 5. So there are kind of two limitations here that we need to look at. So first, we have to see this top. We know it cannot be a, my mouse is in the way. 2 seconds. Okay, we know that from A, that we can't have a negative. Okay, so our x needs to be greater than or equal to 0, and if you see in our graph stops here. It doesn't continue on forever. It stops here, okay? And then if we look, and you can kind of see on your graph, x minus 5, this cannot equal 0. So we know x has to be greater than or equal to 0 because of this. And then we also know that this cannot equal 0. So if x minus 5 equals 0, okay, if x is 5, this gives us a 0 in the denominator, which we can't have. And so what this gives us is called a vertical asymptote. And our graph will not go near this vertical asymptote. Okay, so those we have two restrictions. And so what we need to do is write both of those restrictions as a solution set. So our solution set is, it starts at 0. We go from left to right. So it starts at 0. 0 is included, so we have a bracket. And then it goes to 5. Okay, because 5 is an asymptote, 5 is not included. It can be anything up to 5, but not 5. And then a union, or it picks back up at 5, and then it goes on, continuing right, to positive infinity. Okay, so that would be B's solution set. And then if we look at C, so this is an area where S is that's the area of an equilateral triangle with sides of S squared. Okay, so if we have our equilateral triangle, it's the square root of 3/4 times S squared. And so if we look at our graph, this is just the same thing as the square root of 3/4 times x squared. So this is just a quadratic. So looking, we have our parabola. This goes on forever left. This goes on forever right. Okay, we don't have any limitations on our x here. We can plug in any number and we can square it. We can plug it, we can square a negative, we can square a 0, we can square a positive, we can square a decimal, we can square anything. Okay, so, and if you look at our graph, there's no asymptotes, there's no holes. It goes forever left, it goes forever right. So what this means is our domain is all real numbers. There's no limitations. We can plug in any number for x and we can get a y value out. So it would be all real numbers. Okay, so this is a symbol for all real numbers. To write our solution set, it's just from negative infinity to positive infinity. And infinity is never included, so those are parentheses. So forever left to forever right. Okay, so those are how you write the answers for domain of a function. Okay, so now let's talk. Let's do another one, I think. Yes, so what is the domain of the expression? And so what we need to do here is we don't have the graph just right there handy dandy for us. So we need to do it algebraically. And then you can check it in Desmos. But again, let's do it algebraically first. So let's think about limitations. We do not have any square roots, so we don't have to worry about negatives, but we have two things in the denominator, okay? These two things in the denominator cannot equal 0, okay? So we're gonna set both factors equal to 0. X plus 6 equals 0, and then x minus 4 equals 0. If we solve for x, subtract 6, that's gonna be a negative 6, and this is gonna be a positive 4. It's always opposite. Okay, so basically x cannot equal negative 6 and x cannot equal 4. So let's write our solution set. So we start from our smallest number, which is infinity or negative infinity. So it's not included, so negative infinity. It's great until negative 6. That's our smaller number, so we'll start with that one. and it's going to -6. -6 is not included, okay? So we're gonna do a parentheses, and then a union, and then it picks back up at -6, okay? It goes from -6 to 4. Then it stops because there's another asymptote, so we have our union, and then it picks back up at 4, and it goes to forever, which is positive infinity, okay? So none of those are included because it can't be a 6 or a 4, or -6 or +4. Infinity is never included. So here we have 3 sections, okay? And so I represented that right here on this graph. So we had -infinity to -6, union, -6 to 4, union, 4 to infinity. And so at -6 and at 4, we have what are called vertical asymptotes, and we'll talk about those in a second. But so we have 1, 2, 3, whoa, -1, -2, 3, 4, -5, -6. So we have -6 vertical asymptote. And if you see, our graph goes from -infinity and then it gets super close. So an asymptote, think about asymptote. We don't touch it, we stay away. So it goes from -infinity to -6 and it gets super close to the asymptote. And then it picks back up at -6, goes super close to there, and then it goes all the way down to right here, which, oh, 1, 2, 3, 4. Oh, look, that asymptote is at 4. Okay, gets super duper close, but never touches it. And then it picks back up at 4 on this side. It's super close, and it goes away, and then it goes to positive infinity. Okay, and so the reason why there are 3 unions, there's 3 sections of our graph, here, here, and here. So it's from -infinity to almost 6, -6, between -6 and 4, and then 4 to infinity. Okay, so again, I think visually it helps to see those. Okay, so now let's talk about points of discontinuity. Sorry. So from left to right, if it's continuous for all of x, that means there are no holes. So like parabolas. From left to right, we're good. No issues, we're good. Left to right. If we look at, we have 2 removable discontinuities. So if we go from left to right, we go, oh, look, there's a hole. It's removed, it's up here, and then it's go. So that's kind of like a piecewise function right there. And then if we have just removable, where we don't have a peace sign, that just means that there's a hole there. So basically, if you have like a factor that can eliminate, that's where you can get a hole. Here is a jump discontinuity. So it goes up, down, oh, there's a hole there, but it picks back up here. So again, kind of like a piecewise function, which is 2 graphs into 1. And then here's infinite discontinuity. So we go from left, so here we have an asymptote at A. Okay? So those are just 2 graphs they're not continuous at all. From left to right, they do not continue. These do kind of, 1, 2, 3, 4, they just jump or they have holes, but like these 2 parts of the graph do not connect. And like the previous example we just did, those would be an infinite discontinuity because those 3 sections of the graph they don't connect. They're not continuous from left to right for all values of x. Okay, and so then we're gonna touch on increasing and decreasing. You're not gonna have any homework questions on this. It'll be on next week's lessons, but I wanna talk about it. So if we talk about increasing from left to right, so a lot of the things we're talking about with our x values. So like domain, those will have, parameters on stuff. And then we look from left to right, domain is x values. Whenever we talked about our discontinuity, those looks from left to right, all the x values. Here, increasing and decreasing, also we talk about our x values. So if we look at this graph from left to right, it's always increasing. It may go slower and it may kind of stall out, but it's not stall out. It's going to continue increasing the whole time. If we look at this graph from left to right, it's only decreasing. It just keeps decreasing. It may level out more, but it's still going to decrease. Okay, constant would be just no increase, no decrease, just moving constant. And then you can also have some that are increasing on different intervals. So like this one, it's decreasing from negative infinity, and then right here, it stops decreasing, and that's at -2. So we represent that by this solution set. So negative infinity to -2. And then from -2 to +2, it's a constant. And then at +2 to infinity, positive infinity, it starts increasing, okay? So you can have different levels. And so on tomorrow's lesson, on 1.3, we're gonna be talking about stating this right here, the intervals on which it's increasing or decreasing are constant. Okay, but I just wanted to introduce it today because it kind of fits. And so then let's talk about analyzing a function for increasing and decreasing behavior. Oh, we're gonna do an example of this. So for each function, tell the intervals on which it is increasing and which it is decreasing. Okay, so you're gonna need to graph it. Get your graph in Desmos. Graph it and visualize it. So looking from left to right, trace it if you need to. So I'm tracing my graph and I am decreasing. I'm decreasing to here. And then we start to change. Okay, so that's like my vertex of our parabola. That's our turning point. So we are decreasing from negative infinity, and we stop decreasing at -2. So at -2, and that's included. And this is decreasing. And that's the only section that we're decreasing, so we just write that. And then if we're increasing from here, which is again -2, up to positive infinity. So -2, it's included, to positive infinity. Okay, so just labeling where it's increasing or decreasing. So now let's talk about bounded. Visually, again, a lot of this is visuals with our graphs. So Desmos, you're gonna need to do and utilize. So if we look at this graph, so if something is bounded, that means it doesn't continue down forever or up forever. Okay, so it's bounded to your x-axis. And so if we look at some examples, so if we look at this example here, this is forever gonna go up, and it's forever gonna go up. It's forever gonna go down, it's forever gonna go down. So this is not bounded to our x-axis at all, above or below, okay? If we talk about this one, it says, so these right here are gonna go forever up, this is gonna go forever up. But if we look below the x-axis here, it goes down, up, down, and up. So there's an ending, so it's bounded here. Okay, so this is not bounded above because it goes up forever, but it is bounded below. It doesn't go down forever. Okay, and it also, you can flip that. If you look at this one, if we trace it, it's gonna go down forever. It's gonna go up and back down, then back up, then back down, and forever. Okay, so if you look at this one right here, it's bounded above. It doesn't go forever up. So it's bounded above, but not bounded below. Okay, and you can also be just completely bounded above and below if we look at this example. So if we trace it, it starts here, and that's a point, and that's a point. Okay, it goes up, down, up, down, up, down, up, down, up, and then stops. Okay, so it doesn't go forever up, but doesn't go forever down. So this one's just completely bounded. Okay. I think about like bounded, kind of like grounded. Okay, so if you're grounded, let me go back. If you're grounded, you can be set free, okay? Or if you're not grounded, you can be set free. Like not bounded, you're going on forever. If you're bounded, you're stuck. This is like home. Home base is your X value. You're stuck at home. Bounded is grounded. Okay, if here, that's bounded above because it's stuck at our home base. Okay, hopefully that will kind of help. Bounded means grounded, okay? So let's talk about some examples. So again, we're gonna identify is bounded above, below, or bounded. So neither a bounded above, bounded below, or just completely bounded. So if we look with A, we've graphed it. It's going forever up, so we go up, down, up. And so we look at our home base. Okay, this, it's going forever up, so it's not bounded above. But if you look here, it doesn't go forever away. So it's grounded to home, so it's bounded below. Okay, next example. So it's kind of hard to see, but these are going to keep going up, and these are going to be asymptotes. Okay, it's forever approaching x. Your x home kind of started to go away, but our home base of x axis, it's not going to go back out. This is all it does. So it's bounded to those points. So this is bounded above and below. So you can just say bounded. Bounded. Okay. Let's talk about max and mins. Okay. I feel like visually these are super easy to see. When I'm teaching Algebra 2, some students struggle with it. So if we have a graph, like this example right here, this figure, it suggests that we have point P, we have point Q. Don't know, I'm using blue on blue, P, we have Q, and we have R. Okay, and so for tracing, we go up, we have a turning point, and then we go back down. So this turning point right here is a maximum, because that's the point, that's like the top of our hump. And then we go down, and we have another turning point, and then we go back up. So that would be a minimum. And then we go back up, and that R, this would be a maximum. Okay, and so here we have 2 maximums and 1 minimum. So this right here is called your absolute, because it's like the highest maximum. So this would be your absolute maximum. Okay, and so when you have your graph, this is still a max, but this is maxer, more max. Okay, and then we only have 1 min. So that would be your, it goes on forever, so it would be your absolute min. Okay, because this goes down forever, so that's why this would not be your absolute minimum of your graph, because our graph keeps going down. But it still is a minimum of that turning point. So if we looked here, it says, use a grapher to find all local maxima or minima in the values of x where they occur. So we're given this. You're going to type this into Desmos. You can type that one in as it is. And we have this graph that pops up. And these little gray dots in Desmos are going to pop up. And like, here's our zeros, right? At negative, well, no, that's -1. And at 2, those are your zeros. We don't care about that. We're looking for maximum and mins. So that would be right here, your turning point. Okay, and we're looking for the x values. Well, that's just 0.5. Okay, and so it's the bottom, it's the minimum part of our graph. So it's a minimum, and it's at x equals 0.5. And our y is -2.25. And so it will ask like what your x and your y value is, and you will have to say whether it's the maximum or the minimum. And this is the minimum. Okay. So asymptotes. So we I've already talked about asymptotes a little bit, but let's figure out, some more about finding asymptotes. So if we consider the graph of the function, f of x is equal to 2x squared over 4 minus x squared. And so here we have 3 sections of our graph, okay? So it's kind of here, and so if you see it's gradually approaching, that means it's gradually approaching an asymptote. And so if we drew a vertical line, or not a vertical, a horizontal line, that would be at -2. So this has a horizontal asymptote at -2. Okay, and then if we look at our vertical asymptotes, and we look here, it would be at 2 and at -2. Okay, so your vertical asymptotes would be at x equals 2 and x equals -2. And then your vertical asymptotes would be at y equals -2. So V8, I said V8 for both, wow. HA. So VA is vertical asymptotes. HA is horizontal asymptotes. And so we're going to talk about algebraically how to find those. I very roughly talked about vertical asymptotes is when our denominator can't equal 0. So if we set, 4 minus x squared equal to 0, well, I'm going to do some manipulating. -x squared plus 4, I'm going to switch out, so that factor out that -1 to make x squared minus 4 equals 0. Okay, that is the difference of two squares, so x plus 2, x minus 2, set those equal to 0. That's how we get our 2 and our -2 algebraically. That's how we get our vertical asymptotes. So your vertical asymptotes are when denominator can't equal 0. Okay, so we've talked about that kind of, but that's, some more examples. Your horizontal asymptotes, you have to look at your leading coefficient or your leading powers in your top and your bottom, and then to look at the leading coefficients to figure that out. And so if we have, I'm going to skip on to look at the actual definition. And so let's find some more horizontal or vertical asymptotes. Okay, so what are the vertical asymptotes for the graph of y equals x plus 1, and then x minus 2 and x minus 3? Okay, so vertical asymptotes are denominator cannot equal 0. Okay, so this can't equal 0. So we're going to set each factor equal to 0. Okay, so x minus 2 equals 0 and x minus 3 equals 0. So if we solve, we get that x cannot equal 2 and x cannot equal 3. So our asymptotes would be at 2 and 3. Okay, if we look at, and they're not always going to be factored for you, so you may have to factor the denominator, and I should have done an example of that. So here we have, x minus 1 and x plus 3. So here, our vertical asymptotes would be at x equals 1 and at x equals -3. For B, we have our vertical asymptotes would be x equals 2 and x equals -3. Okay, so we graph those. There would be vertical asymptotes on those x values. Okay, now horizontal asymptotes is a little bit different. And when I say a little bit different, I mean entirely different. Okay, so you compare the degree of the top to the degree at the bottom. So the numerator at the top, m over n. Okay, so the numerator, the degree, and so the degree means exponent. If you don't remember that vocab word. So degree is the exponent at the top to the exponent at the bottom. And it's the highest exponent. If the bottom is bigger, your asymptote is at y equals 0, the x-axis. If your top is bigger, you do not have a horizontal asymptote at all. And then if they're equal, you look at the coefficients in front, and that is your asymptote. So if we look here at y equals 2x over x minus 3. So we're looking for the highest degree. So this is a 1 and this is a 1. So 1 over 1. So here we have m is equal to n. Our numerator is equal to our denominator. So if m equals n, then we look at our coefficients. So in front we have a 2 over a 1. So here your horizontal asymptote is y equals 2. Y equals 2. Okay, looking at B, our top degree is a 1. Our top degree is a 2. Okay, so here we have m is less than n. So our bottom is bigger than our top. So if m is less than n, our asymptote is at y equals 0. So that horizontal asymptote is at y equals 0. Okay, I want to go back to our first one real quick. Okay, this one. Remember we solved for the horizontal asymptote, vertical asymptote, not our horizontal, and I want to show you mathematically now, knowing what we know. We know our horizontal asymptote is -2, and how we get that is the degree at the top is 2, highest degree at the bottom is 2. So since m is equal to n, we look at our numbers in front, our coefficients. So 2 over that negative 1, which simplifies to be y equals negative 2. And that's exactly what we got right there. Okay. So I think that's it. So we have 10 total questions on your homework. Use Desmos. It's going to save your life. So let me know if you have any questions.